Welcome everybody to another session of SCM, and in this session we are just continuing the analysis part of the band structure. So before that, in the previous session we have done the setup of how to run the calculations. So first I have gone through the initial settings of setting up the geometry by introducing the molybdenum disulfide monolayer. So later that I choose this level of theory. So the band engine based on the density functional theory requires the selection of an appropriate exchange correlation function, for example LDA, GGA, and the choice of the function influences the accuracy of the electronic structure. So the user need to choose the basis set which describes the electronic wave function. So band uses slider type orbitals and various basis set qualities, for example SZ, DZ, DZP, etc., which are available. Higher quality basis set generally provide more accurate results at a higher computational cost. And speaking about the relativistic effect, especially the spin orbit coupling, can be significant for transition metal compounds, for example, in the case of molybdenum disulfide, and should be considered particularly for accurately determining the band gap and splitting of the bands. And then defining the K point path. So the K-space integration. To calculate the band structure, we need to specify the path along the high symmetry points in the Brillouin zone of the molybdenum disulfide monolayer. The common high symmetry points for this external 2D lattice includes sigma, gamma, K, and M. The calculation will determine the energy eigenvalues for electronic bands at each K point along this path. So the density of the K points along the path influences the smoothness and details of the resulting band structure, so that I can show you in this typical example that how it will like. So this is actually the band structure where we have defined the K points. So as I said, the commonly high symmetry points for this external 2D lattice. So this is an external lattice in the standard path, and you can see the gamma, K, and M. These things I will brief shortly. So for running the calculation, we can use either the GUI or command line interface with the input file, which we have already run. So analyzing the results, the output, as we are seeing just now, will contain the band structure typically visualized as a plot of energy versus the K point path. So this is actually the energy and the K point path at the bottom. You can see the gamma, K, and M points. So the key features to analyze this band gap includes, first one, the energy difference between the highest occupied band, most obviously the valence band maximum, and the lowest unoccupied band, the conduction band minimum. For this monolayer, molybdenum disulfide monolayer, we can observe the direct band gap typically located at the K point. So this is actually the K point of the Brillouin zone, and the band dispersion, the shape, and the curvature of the bands, which are related to the effective mass of electrons and holes. Then valence and conduction band edges, the energy levels of the valence band minimum and conduction band minimum, valence band maximum and conduction band minimum, which will determine the electronic properties of the material. Then the spin orbit coupling, if the SOC or spin orbit coupling was included, we might observe a splitting of the bands, particularly at the valence band maximum at the K point. And in this case, we didn't mention about that relativistic effects. We just gone with the scalar. So if we opt the spin orbit coupling, definitely we can focus on the point which I have mentioned about the spin orbit splitting. Then the orbital contributions. The band often allow the user to project the band structure onto the atomic orbitals of molybdenum and sulfur in this case, providing insights into the origin of electronic states. So in this image itself, we can see that what is the atomic orbitals of both metals, or this molybdenum and sulfur was considered. And then in the context of this band structure calculations of the material, We have mentioned about the hexagonal 2D lattice. So this is actually the hexagonal 2D lattice. Like the molybdenum sulfide monolayer, the notation gamma K M refers to specific high symmetry points in the Brillouin zone. So to understand the means, we need to break down these concepts into real space lattice as well as reciprocal space lattices. So that part I will brief in the next video. Thank you.